Hello everyone. So today we're going to look at the second Newton's law. It's called the Newton's second law. Okay, now, so from the first law, day one, we learned that if there's no net force, an object remains at rest if it was originally at rest, and an object will continue in motion if it was in motion to begin with. So then the logical question that someone will ask after this will be, well, what happened if the person or the object does not have F net equal to 0? What if there is an unbalanced force? So Newton's second law deals with exactly that, which is what happened when there is an unbalanced net force. Okay, so when you have an unbalanced force will always result in the objects starting to change its motion, which is called acceleration, right? When an object changes motion, for example, speeding up or slowing down. So an unbalanced force always create acceleration. Okay, so when the force is balanced, it's either constant speed or stationary. When the force is unbalanced, you will get an acceleration. Now, this is commonly stated as a formula that you will find in your formula sheet. Okay, which is, so when there is an unbalanced force, so when there is an F let, okay, it will give the object, which has a mass m, an acceleration a. So F net equals to ma. Okay, F net equals to ma. Now remember, force and mass and acceleration, they're different. Force is a vector, it has direction. Acceleration is a vector, it also has direction, but mass is not a vector. So in this case, the direction of the net force must follow the only other number that has directions in the equation, which is the acceleration. So the force and the acceleration have the same direction. Okay, so let's say your net force at the end is going north, then the object will accelerate north. Okay, they have the same direction. Now, notice the unit of this calculation. Mass is measured in kilogram. Acceleration is measured in meter per second square. Force is measured in Newton. So therefore, the unit Newton is actually kilogram times meter per second square. Okay, so kilogram meter per second square is the same as the unit Newton. Okay, so now this is just a calculation problem. So we're going to go through a couple of calculations. So the idea is this. When you're looking at a question, first you want to ask yourself, can I draw a diagram? And then once you draw a diagram, you ask yourself, are the forces balanced? If the forces are not balanced, then you find out which force is the odd one out at the end. You sometimes might have to subtract the forces in order to find who is actually left at the end. Then you apply Newton's second law equation, F net equals to ma, to find out the acceleration of the object. Finally, after writing down the acceleration of the object, please also write down the direction, which is the same direction as the remaining force or whoever force wins. First example, a 5 kilogram block is pushed to the right hand side along a frictionless track with a force of 10 Newton. So frictionless means no force of friction. So a block is being pushed to the right hand side. So someone is pushing that block. We call this an applied force. Applied force is just some kind of a push, applied force. Now, but remember, so if you remember from the example that we talk about, everything is basically just electrostatic force. So applied force is, of course, just electrostatic force too. So you have to think about, hey, okay, what if someone from behind is pushing that block? Well, then the electron on its hand is repelling the electron on the left-hand side of the surface of the block. So therefore, it creates a repelling force that goes to the right-hand side. This is called applied force. Okay, force of apply. Someone applied this force to it. Now, how much is that? According to the question, that is exactly 10 Newton. Now, what else we have in this picture? Of course, in every question, as long as you are not in space, very far away from the Earth, there will be force of gravity. Even if the object is in the air, there's always a force of gravity. Force of gravity on Earth never ceases to exist. Now, but if you look at this picture right now, it doesn't make any sense. If you look at this picture right now, the overall resultant force, if that's the end of it, right? The overall resultant force will be something that points like this way, which means that the block will submerge underground and get buried. You know in real life that it doesn't happen. That means this picture is missing something. It's missing a force that's countering gravity. Now, this force, as we learned yesterday, is the normal force. Do not mistake the normal force from the net force. Normal force, we use capital N. Net force, we spell out the word net. Now, you look at this picture, normal force and gravity has to balance each other. Because why? Because of logic. When you put something on the table and you try to push it to the right-hand side, does the object suddenly start flying in the air? No, it doesn't, right? Or submerging underground? Okay, that's very scary if it does, okay? So, it usually doesn't do that. That means force of gravity and normal force usually cancel out each other in this situation. Now, you look at what is the net force. Net force, remember, is not an actual force. Net force is whatever that's left. Gravity and normal force committed suicide. So they kill off each other. So they cancel out. So the only force that we actually have left is the applied force from the person pushing. So the net force in this case is the applied force, whatever that is. Now, but remember, net force equals to mass times acceleration. When there is a net force, the object will accelerate. So F net equal to ma. So I can replace F net with ma. The applied force, according to question, is exactly 10 Newton. So we put 10 over there. And do we have the mass of the object? Yes, we do. It's a 5 kilogram block. So we put 5 kilogram in here. Multiply by this unknown acceleration is equal to 10 Newton. Okay, so finally, we get the acceleration by dividing both sides by 5. So the acceleration of the object is 2 meters per second square. Now, this is just getting its magnitude. We also have to look at the direction. Which force is winning? Well, it's the applied force that's left at the end. Which way is the applied force pointing at? The right-hand side. So which way will this object accelerate? The right-hand side. So we put the right-hand side as the answer, and this is the final result. Pretty easy, right? So you have to follow this rule. Usually a diagram will help. There is going to be an entire page of notes on drawing diagram just after this, and writing down the F net, finding out what F net is in this equation. In this question, F net could be anything. Sometimes it's one force, sometimes it's two forces subtracted, sometimes it's two forces adding together. Imagine two people pushing the box, right? Net force will be the combination of the two. And then you replace F net equals to ma, and you replace the force by finding the numbers. At the end, divide both sides by the mass of the object and find the acceleration. So it's generally pretty easy. Keep going. If a 650 kilogram car accelerates at 4 meters per second south, what's the net force acting on it? Now this one doesn't even need a diagram. F net equals to ma, and the question just gave me, well, the mass, which is 650 kilogram, and the A, 4 meters per second square. The unit works out. So to find out the resultant, the net force, which is whatever remainings on it, the net force is roughly 2600 Newton. But we need a direction. Since the acceleration is to the south, my net force is also to the south. Okay? Now, I might, if you really want to, you could add a negative in front when you're writing down your acceleration, because that's to the south. And then at the end, you will have a negative in your answer. So technically, as long as we kind of remember that it must be the same as the acceleration, we don't really have to put negative in the number that we are plugging in. So that's it. I write south, right? You don't write negative of south. That's double negative. Let's see how we're going through this faster, right? A 1500 kilogram ice cream truck accelerates from the rest to a top speed of 45 km per hour. Ew. Immediately upon seeing the km per hour, we go ew because the rest of the question is in second and presumably also in meter. So our first step is not actually solving this question, is to finding out what is V final. So V final turns out to be, whatever 45 meter per second is divided by 3.6, which is 12.5 meter per second. Now, the object starts from rest, so assuming V initial is 0. Okay, and time is, 8 seconds. What are the question looking for? What is the net force? Now, the question wants us to find net force, but we are writing a whole bunch of speed, initial, speed, final, and time. We're not doing any forces. What we're trying to do in here, we're trying to find acceleration. Why are we finding acceleration? Because according to Newton's second law, if there is an acceleration, there must be a net force. So if I can find its acceleration, then multiply by mass, I will get the net force. So moving down in here, we are going to solve this equation with kinematics. Hey, kinematic makes a comeback again. Now, hopefully, all of these is easy. So there, V initial is 0, acceleration is 8, is unknown, time is 8. Divide both sides by 8, acceleration is done. 1.56. Okay. Now, meter per second square. I'm keeping more decimal point than I usually do because I know this is not my final answer. My final answer lead this acceleration. So we're going to use that acceleration in the next part. So in the next part, we use Newton's second law. F-flat equals to ma. Okay, so now we have acceleration. We want to find net force. Put the mass in. Put the acceleration in. And multiply them. So F-flat is about 2,344 Newton. That's the net force at the end. Okay, so I rounded off the decimal point. So you don't need that many decimal points if your answer is already big. And if it's the final answer, you can always round off stuff. I'll just say don't round off anything if it's not the final answer yet, right? So to find net force, we have two different approach. If the two or many forces are working together, that means pointing in the same direction, we add them. So we add them up to find net force. Well, what if the two objects are not, the forces are not working with each other? Well, in that case, if the forces are working against each other, then your net force should be whichever force that wins minus the forces that are pointing in the other direction. Okay, so you have to pick like which side is bigger to determine who is the winner. And then you do the winner force combined minus the losing forces combined. Okay, example. All right, Stan and Kyle are pushing a 75 kilograms sled along a frictionless ice rink, so no frictions on that. Stan pushed it with 55 Newton, Kyle pushed it with 45 Newton. Find the sled's acceleration. So we basically have two applied force instead of one. So we had the applied force from Stan, and then we had the applied force from Kyle. Okay, so the force for Stan, the applied force for that is 55 Newton. The force for Kyle, okay, so the force for Kyle is 45 Newton. And then what are we missing? Force equality, we always have it, and normal force, which is always the same and opposite. Okay, so you look at this picture, and Fn and Fg normal force cancels out. So the Stan So Stan's force and Kyle's force are working together in the same direction. So in this particular case, F net is equal to the force of Stan plus the force from Kyle. Okay, now then F net equals to MA as usual. 55, 45. All right, so add up together 100 Newton. So the mass of the sled is 75 kilogram, and we're trying to find acceleration. So divide both sides. 1.33 meter per second squared. Direction. Pushes link. Okay, so the question doesn't actually give us any direction, so positive, whatever it is. Okay, because if you look at the question, they didn't really say which direction is positive. So we can't really just guess that. That would be it. Okay, next one. Batmobile. The Batmobile exerts a force of 8.5 times 10 to the 3 Newton east. That's just 8,500. I don't know why they say it that way. It's not like it's saving that much time. While friction pulls back on it with a force of 1,500 Newton. If it has a mass of 1,250 kilogram, what is the acceleration? So the Batmobile is like a rocket car. So imagine you have a car, and then someone strapped a rocket on the back. Okay, so now a couple of things we know, which is force of gravity and normal force is paired. Okay, so normal force, force of gravity. All right. Now, the pi force is to the east at 8,500 meter. Okay, so the pi force that someone is like pulling it. So let me see what I call this one. This one is the, okay, so it's just from the Batmobile, right? So that's the pi force from the Batmobile. So it's 8.5 times 10 to the 3, which is 8,500. Now I don't need to know about how much this 2 is because it will be included as like something that cancels out already, right? And now we have one other arrows to draw, which is friction. So friction turns (1,500) Newton. So that's your force of friction. Okay, so this game, then, we actually do have two people fighting. The pi force and the force of friction. Now, one is going to the right, one is going to the left. So which one? Oh, I shouldn't put negative because I have an arrow that says it goes to the left already. So which one should win? It should be obvious. Winner is the bigger force. So therefore, let's say right-hand side wins. Then your net force equation is going to set up this way. So your net force, okay, is going to be a pi force minus friction. Okay, and then a pi force, F net equals to MA. Right here. Right here, like that. Subtract them. Now the mass is made up from the question. Okay. Oh, sorry. This is actually 7,000. Now divide both sides by 1.25. Acceleration, 5.6 meter per second square. And direction. Which way does it point? East is whoever wins. All right, and that's the final answer. Okay, so now we've done a couple of questions of that type. Now these questions could get harder sometimes though. So we are going to look at worksheet 4.2. So now let's look at the second page of the worksheet number 1.2, 4.2 on the Newton's second law. Now, first of all, when you read this question, the first thing you realize is, hey, that speed doesn't look too good. So what happened is we can then say, okay, so we will change the meter per second, km per hour, to meter per second to make it look nicer. Okay, so that's the first thing we do. Change the meter, km per hour to the meter per second. Okay, now then the second thing you can do is draw a free body diagram. So it says this question is a skydiver, 75 kilogram, falling at terminal velocity before pulling the parachute. Now, once you pull the parachute, you slow down to 25 km per hour in 3.8 seconds. Determine the average force of friction, air friction, that's acting on her during her deceleration. So basically, once you open the parachute, the air resistance is even greater than gravity. That's why you are able to slow down. So before you open the parachute, you speed up to a point where the air resistance and your force of gravity is exactly the same. Then at that point, you reach something called terminal velocity. Now, but afterward, you will continue to go down, right? And what happened is, if you want to decrease your speed so that you don't hit the ground as fast, you will need to open the parachute. So when you open your parachute, this is what happened. So the force on you is going to be, of course, force of gravity going down, and you have big air resistance going up. Now this object is in the air, so therefore not normal force. Normal force require you to be sitting on the surface. You're not sitting on the surface right now. Okay, so these are the two forces when you're comparing. Air resistance versus force of gravity. Now for force of gravity, that's easy. Fg equal to mg, and the mass is 75 kilogram, and the gravitational acceleration is 9.8. So once you get these two combined, you get a force of gravity that is about 735 Newton. Okay, so this is Fg, roughly 735 Newton. Now, what else is on there? So another thing that I know is, if I read the question, so I have no idea what the air resistance is. So the average force of air friction, that's exactly what we want to find in here. But I have no idea what that is. So how do I approach this question? Right now, at this moment, you're actually stuck. Okay, so we will leave this space in here using the bottom to write this. Because right now, I can say the net force of this object is, because you're slowing down, so the air resistance is actually greater than force of gravity, so you should be subtracting them, because force of gravity is going down and the air resistance from the parachute is going up. So you look at who is bigger, right? Well, if you're slowing down, then the one pulling you up is bigger. So we always use the bigger one and subtract by the smaller one. Now, then you have this, right? We replace the F net with MA, and then we try to put everything in here. So air resistance minus, 735 Newton. But here is when you get into trouble. Because looking at this equation, you also have mass, which is 75 kilogram. But you don't have the acceleration, right? So you know the mass is 75 kilogram, but you don't have the acceleration, and you don't have the air resistant force. So you cannot have two missing things, right? That's not something we can solve. One equation, two missing things. Now, what I really want right now is the air resistance. So that means I have to find my acceleration some other way and substitute into this equation and get my air resistance later. How do you get acceleration? If only we have equations that can find acceleration given initial, final, and time, right? If we only have something like that. And we do. That's called kinematics. That's why unit 1 and unit 2 are linked together. Now, this person has a velocity of 61.1 meter per second, repeating 1. And then it slows down, which is then a V final. So V final slows down to a 25 km per hour, which is 6.94, repeating 4 meter per second. And this all take place in 3.8 seconds. And looking for acceleration. Now, this is easy. One of the basic equations for kinematics can do it. V final equal V initial plus AT. And we're solving for A. Okay, so some algebra later, when you substitute the numbers in, so the numbers such as V final equal to 6.94, V initial equal to 61.1, acceleration unknown, time is 3.8. So after some algebra, the acceleration is now some value that we can use. So let me go in here and write down the acceleration at this point. So the acceleration turns out to be negative 14.25 meter per second square. Now, with this acceleration, what we can do is substitute that into the equation for the net force. Okay, you see where this little a is? Now we actually know what that little a is. And we can substitute that and then go on and solve our air resistance. So 75 times, so the net force is, now, so what we don't have to do is we don't have to put the negative in it because we already know that friction is winning. Like air resistance, friction is winning. Air resistance is winning. So the object is slowing down. So the net force is a negative number. But because we took the top minus the bottom, so technically speaking, we don't need the negative in there. So we just need the air resistance. So with the acceleration, 14.25, we know that it's coming from the air resistance force minus the 700, minus gravity, 735. So now solving for air resistance, which is roughly, if you do sig fig and everything, 1,800 Newton. Okay? So now it makes sense. But write the number up top. See? 1,800 minus 735. So the force that goes up is stronger than gravity, which goes down. That's why you are slowing down your descent. Your descent is going down, but your acceleration is pointing up. So if your descent is positive, then technically your acceleration is like a negative value, right? So that's why it gets really confusing. We don't put negative in the acceleration in the equation, right? We just look at it and you go like, okay, well, obviously the force that's winning is 1,800. The force that's losing is 735. So when they subtract, you have a net force, and that net force gives you an acceleration, and the acceleration is 14.2. Which way? Well, upward. Well, how come upward? Because you're slowing down while you are traveling to the negative side. Okay, so now there's some, I think, corrections on the answer key. So I do believe that these are, the first one like is over here, and then the second one is over here. Okay, so you should definitely try some of them. These are your new type of calculation, which is calculating acceleration. It's not the most obvious thing, so you want to try it. And we're most likely going to have a quiz on these type of questions very soon. Okay, so now I'm going to go and move on to the worksheets. Now I've been drawing these diagrams a lot. Now these diagrams actually have a proper name. They are called free body diagram. Okay, so we are going to switch into the note that says FBD. So FBD stands for free body So free as in freedom. So free body diagram. So free body diagram is a technique that physics people use in order to represent a regression drawing all the forces on an object. So now in a free body diagram, here are some of the rules. In the free body diagram, you will draw all the forces as an arrow with a little head, starting from the center of the box. Okay, so I don't want to see a diagram where you draw a force pushing down like this. Okay, so if there is a force pushing down like this, okay, so this is the not the correct way to do it. So if there's actually a force pushing down like that, please do it this way. So draw the force from the center of the object, kind of from the center, and going this way. Just make the same directions. Okay, so draw the force this way instead. So instead of into the force, into the box, it should always be coming out of the box. Now, for any object, just draw a box. For example, the question says a car, a box. Person, a box. A cat, a box. Okay, anything you can represent it with a box or maybe a circle. That's your object. These type of diagram is supposed to be helping you just figuring out like directions and everything, and which one subtract by which one is the net force. So like the detail on how nicely you draw the cats or the dogs and the person doesn't really matter. Just the forces. Arrows are the forces. It starts from the center or maybe close to the center, and then it just go out. Okay. Now, here are the forces that you are required to draw. Some of them will be picked up later on in part 2 of this. Some of them you already know. For example, force of gravity. The first one, force of gravity, you already know that one. So no surprise from there, right? So force of gravity. Now, and then we have an applied force. So applied force, remember, is just a electrostatic force in the sky. So F applied, sometimes you just see people doing FA, applied force, which is any kind of a push. So, or pull on something. So any push or pull of an object. So you apply force by pushing it. It's just your electron of your hand repelling the electron from the side of the object. Now we'll jump over to normal force source, and then we'll go back and talk about friction. So normal force, Fn, big N, remember. Now this is the force that's always perpendicular to the, remember normal means perpendicular, to the surface. Okay, perpendicular to the surface. Now you might say, okay, Mr. Chang, that one's easy. It's always going up, right? No, it's not always going up. If the object's sitting on a horizontal surface, which is like 90% of the case is, because, you know, it'll be on the ground, then yeah, normal force is pointing up. What if you have a mountain or like a hill, like a slope like this, and the object is sitting like here? Okay, so this is your box. Which way does normal force point? Now you have to remember, what is normal force? The electron of the surface of the object repelling the electron on the surface of the surface. Okay, that comes out weirdly, but that's exactly what it should be. So is these electrons repelling the other electrons? So which direction is the normal force? Perpendicular to the electron-electron interface. So your normal force should be this way. Now remember, normal means perpendicular. So what are we perpendicularing to? We are perpendicular to the surface. Okay, so whatever surface you have, we are perpendicular with the surface. So it is not always pointing up. It's not like for us in physics 11, it's almost always pointing up, but it doesn't have to be. Okay, now we have another one. So we are jumping around a little bit, I know that. F air, I call that air resistant. Okay, F air, air resistant. So this is the air molecule slowing you down, because the air molecules are also made of proton, neutrons, and electrons. So they also have electron repelling you as you go through the air. Now, air resistant has a tendency of getting stronger as you move faster. So the faster you move, the stronger the air resistance is. So for example, if you're sitting here not doing anything right now, air resistance is 0. If you're running at 10 meters per second, air resistance might be 500 Newton. But if you're running at 20 meters per second, air resistance will be greater. It will be, 1,000 Newton or something like that. So air resistance, okay, now it gets bigger as you move faster. Now also though, air resistance is always, in terms of direction, against the motion of the object. Now this is very important. What does that mean? That means if the object is going down, so for example, if you have like a ball and force of gravity is making it go down, and this object is going, so let's say this object is going down right now. So I would draw this like line up here, indicating that it's falling to the ground right now, right? Okay, so you know what, I'm not even going to draw gravity. I'll just focus this question on this air resistance. So if the object is going down, so if the velocity is like this way, then friction, air friction, goes this way. Like the air resistance goes this way. It's opposite to the motion of the object. Now what if the ball is being thrown up instead? So for example, you just release the ball, it's still on its way going up. Okay, so it's on its way going upward. So the velocity for now is upward. Then in this case, air resistance is going down. Okay, so air resistance, or air friction, sometimes we call it, is always opposite to motion, to the motion of the object itself. Okay, so always opposite to motion. All right, now keep going. We have the few that we stopped. For example, force of friction. So force of friction, we took it out separately. So force of friction, F with a little subscript F. Now this is like force of air, but instead this is kind of like a surface friction. Now when you rub an object against another one, so for example, if you're at home right now, rub your hand against each other, you can feel the friction slowing it down. Or you push something on the table, slide it on the table, it will eventually slow down. That's not just the help of air resistance. That's also the help, the force, in addition to air resistance, there's also resistance coming from the fact that you have two surfaces rubbing against each other. One is trying to slide past the other one. So this ideally is the surface friction. Okay, and this is also, of course, against motion. So if you slide an object to the right hand side, the surface friction will be to the left. If you slide an object forward, the surface friction will be backward. As long as you're sliding an object some way, the friction is on the other direction. So for example, you can even see it from like this sliding. Now, so look at this box right now, right? The box that we draw for the normal force. Look at this right now. Now, which way would this box slide? Well, obviously, it's going to slide like this, right? It's going to go downhill. So now the motion of the object is downhill. So what is the direction of the friction on the surface of this? Now, there will be a surface friction because you have one object, the block, rubbing against the surface of the cliff, of the hill. So therefore, there's actually a surface friction in here, which points opposite to the direction of the movement of the object, which is going downhill. Okay, now it's called surface friction, so it's always parallel to the surface. Okay, normal force is always perpendicular to the surface. Surface friction is always parallel to the surface. Now, but of course, remember I told you that only gravity is real. Everything else is this guy from electrostatic force. Well, what is surface friction? Now look at this picture above. So you're pushing an object with an up high force, and there's a friction force going backwards. Let's look at microscopically the two surfaces. Now, the two surfaces might look very smoothly when you inspect it with your naked eyes, but it's actually very rough if you look at it under the microscope. in science class earlier, you must have looked at your own hair or something else through through a microscope. You know that, a very smooth string of hair actually has a lot of dent and imperfections in it. So if you look at the surfaces under a microscopic level, you see that, the surface is not smooth at all. So you actually have a lot of mountains and valleys, like a lot of, indentations and imperfections on the surfaces. So when you rub against one to the other, these imperfections catch onto each other. So those electrons will repel each other, right? So if you're trying to push the object to the right-hand side, then some of the electrons are being forced to get close to each other from left to right. And what happens is they will repel and give you a force that points to the other direction. So friction doesn't always stay in one direction. If I push the object to the right, friction goes to the left. If I push the object to the left, friction goes to the right. Now then, how come ice has minimum amount of friction? So ice doesn't have a lot of friction because ice is filling in those gaps. So let's remember, so for example, if you have like a surface that is like kind of imperfect to begin with, and what happens when you fill it with water is that the water is going to stay as like a layer on top like this, and then once that layer is cooled down enough, it fills in those gaps, right? Because water takes the shape of the container. So it fills in the gap of those imperfections on the ground. Therefore, it gives you a pretty smooth surface. Now, of course, it's not perfect. Nothing is perfect. That's why you still have a little bit of friction. But it's better than, the ground picture, right? It's smoother than the ground picture. So that's why ice, or very polished surface, has lower friction. That means it's easier to slide against it. Okay? Now, we will put more emphasis on friction. There's even an equation for it. It will be on part 2 of this of the note. Okay, so now friction done. Tension is another thing. So tension, sometimes you say T, sometimes it's F of T. So F and the little subscript T. Tension is the force on, so the force along a rope or wire. So now a rope or a wire is held together by the bonding, the chemical bond of the protons and electrons and neutrons, right? So you know how in chemistry we say, well, things bond together if they're sharing electrons and then form this like covalent bond or ionic bond. Now, this is the reason why things stay together. Like a piece of wood doesn't become like a soup of proton, neutron, electron when you pull on it. They have a little bit of staying power, like a rope or anything, right? They have a structural staying power because there are internally chemical bond that's holding them together. Now, that chemical bond that's holding them together is technically electrostatic force, right? Again, it's proton and electron holding on to each other in a structured way, sharing electrons sometimes, sharing protons sometimes, right? So yeah, this is still a electrostatic force in the sky. Now, for tension though, however, it depends on the point of view of where you're looking, which part you're looking from. So for example, you have a ceiling and you want to hang something on it. So you have like, you bought a rope, right? So you go like, okay, I have a rope. This is my rope. And then you can put like a commercial sign or whatever on the lower end right here. So we're looking at the object from the side, okay? So ground is in the bottom. So now look at the diagram on here. So we have force of gravity, of course. Anything with mass has force of gravity there, right? And now if this is the only picture, then nothing is balanced in here. The object will go to the ground and accelerate, right? So there must be a force pointing up to counter that. Now the force pointing up to counter that is called tension. It's a tension on the wire that's holding it up. Tension. Okay, and it will be exactly opposite if the whole thing is not moving, right? To gravity, and same matter to opposite direction. So this is the rope. Now, so if you only look at this object, the whole thing is balanced out. Okay, but this is the point of view of the box. So if you ask the box will say, oh yeah, gravity is pulling me down, the rope is pulling me up. That's what the box will say, right? Well, what about the ceiling? You know, the ceiling has feeling too. The ceiling also feels. So if you ask the ceiling, right, the ceiling is going to say, hey, someone is pulling down on me. And that is also tension. Now, that number has to be the same as the tension that the box felt, because it's the same tension, just from two different point of view. So if you ask the ceiling is saying, the top, the roof is going to say, hey, yeah, there's a force pulling me down. If you ask the box say, no, there's a force pulling me up. Well, they're the same force. You're just talking about it in two different people's point of view. So same thing as tug of war. So in tug of war, you think the other person is pulling you to the right, the other person thinks you are pulling you to the left. Technically, the tension is the same number, just in opposite direction. So it's exactly like tug of war. So it's always two different ways of looking at it. All right, tension. Now, last is going to be elastic force, and that is going to be a force that we will talk about, I think, at the very end of the chapter when we get to it. So elastic force, or sometimes we call it spring force, because elastic force is from spring, like an elastic band. So elastic force is the force on springs. So if you have a spring, or if you have like a elastic, like a bungee cord, a elastic rope, or a elastic band that you might have at home. Okay, so now that is a restoring force. So that's a force that's almost like tension, but instead of tension on the wire, it's the tension on the spring. Okay, now that we will spend a lot more time talking about later on when we actually go to part 2. So for now, just note that this is the force on the spring. Okay, you won't even see it on this page, I believe. So you should be okay. So then we will go very quickly into looking at these examples and drawing the appropriate free body diagram. Now remember, free body diagram means a box representing the object and all the forces on it that you can think of that exist. Now remember, you can only use the forces on this list. So if you draw a force, you think that force exists, but you cannot name it, then no, that force does not exist. Okay, you just make that up. So it has to fit one of these 1, 2, 3, 4, 5, 7 definition. If you draw a force, you think, hey, there must be a force over there, but then you cannot name that force because it doesn't fit any of the description in here, then no, there is no force in that direction. You are imagining things. Okay, so I will do 2 examples. First one is a box pushed across the rough floor at a constant speed. Okay, so we do that one. And now so first of all, you have to notice that it's constant speed. Now what does that mean? So someone pushing the object, so let's say to the right hand side, and this is the applied force. Okay, that exists. Now, and then I have force of gravity because on Earth. And then I have normal force because we are on a surface. And how big is normal force? Same as gravity. Otherwise, the box will go up flying or it goes under, which is scary. It says constant velocity. Constant velocity means acceleration equal to 0. Acceleration equal to 0 means F net equal to 0, because the only way you can have constant velocity is if there is no net force. Looking at that picture right now, that doesn't look like no net force to me. I mean, obviously, applied force has no enemy. Well, we have to add an enemy. Well, what could this enemy be? Well, this is a rough floor. So, friction. How big is friction? Because you have constant velocity, all the forces should add up to 0. Therefore, this normal force, this friction should be the same as applied force. This is the free body diagram of an object that's moving at constant speed with friction. Rough floor means you must have friction. Okay, sometimes they will say like frictionless or smooth, then you ignore friction. In real life, there is no frictionless, right? Like perfect frictionless is when you're not touching anything in space. So we can pretend that we have a surface that's almost frictionless just for the fun of it, but in real life, there isn't any. So let's say in the second one, a hockey player glides on a frictionless ice at a constant velocity. So that hockey player, how do we represent a hockey player? We put him in a box. Okay, that sounds horrible. Don't put people in a box, please. especially don't lock them unconscious and put them in the box. But, in the free body diagram, we don't care about the object itself. So just a box. Glides on frictionless ice. Now, frictionless ice means you cannot do frictions on this picture. So now the object is moving, like, let's say to a constant speed, right? So the object must have some kind of a velocity going in, a certain direction. Maybe like going this way, there's a velocity. Now, we don't know what the velocity is, but we know it's constant velocity. So there's no acceleration. Let's draw gravity because we are on Earth. Let's draw normal force because otherwise we fly or submerge underground. And these two should be equal. Now, what else? So some people is going to say, Mr. Chang, I got it. Apply force because the object is moving. No. Because if you draw that apply force there, then there's no longer a way for us to maintain constant velocity, which is F net equal to 0. Because if you draw the apply force on there, we'll have to add friction on the other side in order to balance this out. But the question just say frictionless ice. We can add the friction to balance it out. So that means we also cannot have an apply force. Now, this is one of those situations where you say, but Mr. Chang, how come the object is moving and there's no force pointing in the direction that it's moving? No, remember, you don't have to have a force pointing in the direction that you're moving. If there is a force pointing in the direction that you're moving, you move faster, you speed up. If there is a force opposite to the direction that you're moving, you slow down. If there's no force in the direction that you're moving, you maintain Newton's first law, constant speed. Okay, just imagine in space, I throw you an apple, I let go, the apple no longer has any force forward, but the apple will continue to fly until eternity, or until you catch it. Okay? Now, so what I want you to do right now, at this part of the lesson, is to draw all 11 of these free body diagrams. Okay, so there are 11 on this week. Draw all of them. So you pause the video, you draw all of them, and you come back to the video and you compare the answers. Okay, so that's what you should do. Now, of course, I'm not going to stop. I mean, for me, I'm just going to continue. So you pause the video right now. You draw every single one of these with pencil, so that when you make a mistake, you can actually change it. And come back after you're done with all 11 free body diagrams and compare. Okay? Now, so I'm assuming that, hey, welcome back. I'm assuming that you have paused the video and tried this yourself. So we're going to look at the answer. All right, so let's look at the first one. Now, a book is sitting at rest on the tabletop. So that one should be very easy. Force of gravity balanced by normal force, right? I mean, nothing else should be on there. The object is stationary. Now, it could be sliding at constant speed, but, we don't have to say that because the question is saying at rest anyways. Same magnitude, opposite direction. Next, a girl is suspended motionless from a bar, which hangs from the ceiling by 2 ropes. So someone is like doing the monkey bar. This is like the monkey bar situation. So your 2 arm is supporting yourself. Now, so we have the girl who is that comes out very wrong. The girl is not in the box. The girl is the box. Okay, we're not putting a girl motionless in. Okay, that's getting worse. Like a person motionless in a box. Yeah, no. Don't even go there. Okay, so we have someone hanging, on a bar, like a monkey bar, right? When you go to the playground. So 2 arms supporting the body weight. So the body weight, which is force of gravity, goes down, right? Now, you can see I have 2 tension going up because the 2 arms supporting yourself, not 1 arm. If it's 1 arm, then that 1 tension should be exactly the same value as the weight, which is the Fg. But because you have 2 arms, so each arm can support half of the weight of your body so that they add up together equal to the total weight of your body. So that's why I draw the 2 tension slightly smaller. Okay, they should be half the size of the Fg so that when the 2 tension add together, it will be the same size as the Fg. And egg, number 3, falling from a tree. That's it. Like, there's ignore air resistance, right? Force of gravity. Nothing else is there. We cannot do air friction, which is opposite to the direction of the movement, because they say ignore air. Next one. A plane is flying at constant speed. That means all the forces balanced, right? At the moment they mention constant velocity, you just have to know that every force is balanced. Like all the direction in y balance and all the forces in x balance. So you have a applied force generated by the engine. So I've put it forward, which is of course balanced by air resistance going backwards, right? And then we have gravity. And gravity is balanced by the lift provided by the wing. So the wing actually provides you with some kind of applied force that goes up. Now, in aviation, they call that the lifting force. It's just like an applied force that goes up provided by the wing of the airplane. So I'm going to say lift in here, but it's an applied force, just vertically. Okay? And they should all balance out. Vertical, balance, vertical. Horizontal, balance, horizontal. That's the only way you can have constant speed. Next one. Now, this one is not done yet. So don't worry if you're looking at your picture. A rightward force pointing the book, and the book actually has rightward acceleration. So we have gravity, normal force. Of course, those are our common partners, and these two should be exactly the same. Now, but then we have a force pointing to the right-hand side, and that's the applied force. Okay, there is also friction. Consider friction. The question said, okay, we will consider friction. So friction should be pointing to the left. But how long should that friction be? It should be less than the applied force. How come? Because the applied force should be the one that's winning. Why does it need to win? Because your acceleration is right-hand side. That means whoever that's on the right-hand side should be the winner. Remember, net force? Net force is the winner minus the loser, right? So if the right-hand side force wins after subtracted by the left-hand side one, then you can have right-hand side acceleration after F net equal to ma. Now, in the free body diagram, of course, you don't have to draw the who win. Like this picture right here is the perfect free body diagram. I'm just putting that extra piece of information for you to see. Okay, because I have right-hand side acceleration, I should have the right-hand side force winning. Now, next one, same exact question except that is at constant speed. Now, then in this case, if the question demands that we have constant speed, then we no longer can play the, hey, one side is winning, one side is losing game. So we will have to say that they both equal to each other. So I would say applied force go this way, Fa, but then friction goes the other way, and friction is the same as the applied force. So they should be the same length. Let me make sure that they are the same length. There you go. There, right? They're roughly the same length. You know what I mean. All right. Now, then, moving on. Number 7. Someone who is wearing a backpack on your shoulder. Only by one strap. Now, usually when you wear a backpack, it's 2 straps, right? It will look exactly like the girl doing the monkey bar on a tree question. The one, number 2. But then if you're only wearing your backpack with like one strap, then there's only one tension, right? From the strap is a rope. So therefore, what is on it is called tension. So we have force gravity on the backpack balanced by that one strap, which is tension. Okay, so tension, there you go. And they should be balanced as long as the backpack is not falling down. Next one, a skydiver is descending with constant velocity. Consider air resistance. So it's a skydiver right here, a box. Gravity is making it accelerate downward, but you reach constant terminal velocity. Remember, that's what it's called, because friction is big enough. So what kind of friction it is? It's called air friction. So when the air friction is big enough to combat gravity, you reach a constant velocity situation. So as you jump down from a building, right? So if you jump down from something or you drop something from a place that's really high, the object will initially accelerate. It will go faster and faster and faster. But then that acceleration slows down, even though gravity is still there. Because air resistance become bigger and bigger and bigger. Air resistance scales with the speed of the object. The faster you're moving, the greater air resistance. Now, if you don't trust me, go outside and run. If you're walking or if you're standing still, you don't feel the air resistance. When you walk, you feel a little bit of air blowing against your face. When you run really fast, you feel like a huge amount of friction going against you. See, air friction is opposite to the direction that you're running, and it's also getting stronger and stronger as you go faster and faster. So eventually what happens is you reach a point where your air resistance is big enough that it actually balances out your force of gravity going down. So at that point, you reach a type of velocity called terminal velocity. Okay, terminal velocity or terminal speed. That means this is as fast as you can go. You can't go any faster than that. Most of the time, it only takes like a few seconds for an object to reach terminal velocity. Then it's constant speed going down. So for example, if you drop something from the airplane, it might take, 8-9 seconds for the object to speed up to the terminal velocity, and then it will maintain that velocity until it hits the ground. Okay? It won't go faster and faster and faster and faster forever because of air. Now, of course, if you have a vacuum, then yeah, it will go faster and faster forever. Next one. A force is applied to the right hand side of a sled across a loosely packed slope with a rightward acceleration. So now in this situation, so I guess I have the box and I have the apply force. Well, gravity first. I always draw gravity first. It's like a habit. So gravity, tension, apply force. There you go. Now there is acceleration to the right hand side. So that means even if I draw friction, it will be small on the left hand side, right? So the acceleration is right hand side. Loosely packed slow. Does that mean I don't consider friction though? If they say ice, I might actually not draw friction. This is like debatable, but I'll draw a little bit of friction. Because remember I said, like, in real life, the only place that you have like zero friction is actually space when your object is not touching anything at all. Okay, football moving toward its peak. So that's a football. So it's moving toward its peak. That means it's on its way going up. Okay. Now, so the free-body diagram on that. Now, of course, you're still going to have like gravity. I mean, it doesn't matter which way your object is moving. Gravity is gravity. What else do you have? Which way is your object moving? This way, right? So air resistance go against motion. This object is in the air. So you have, air resistance. It goes against your motion, which means it will go down. So there you go, goes down like that. So air resistance. There, so air resistance and gravity actually works together in this case. Okay, so the last one, car is coasting to the right and slowing down. Diagram force acting on the car. Okay, so the car is slowing down. Coasting means that it's no longer, the applied force no longer exists. Oh, my computer is jumping. I don't know if you guys can see that, but my computer, my tablet is overheating to a point that the screen is jumping right now. Hopefully you don't get to see it because you think your computer has something wrong, but it's actually mine. So your car has a speed going this way, but it's slowing down. Okay, so the acceleration, slowing down means the acceleration is in the opposite direction. Now, so you have gravity normally, so gravity, normal force, which goes up, and no more applied force. But slow down requires friction. So you will have friction. Now, why is friction pointing to the left? Because I have the speed of the object going to the right. Why is the acceleration going to the left? Because the acceleration comes from the only force that's left in here, which is friction. Friction is the only force left. So your acceleration is following the direction of the friction. That's it. So even though the car is going to the right, but when it's slowing down, you're no longer hitting the gas, right? Think about driving. Your gas pedal is the applied force. Your brake is the friction, right? Okay. So you're driving, you're moving forward, you see the red light. So let me ask you this. Which pedal do you press? The gas pedal or the brake pedal? You go with the brake pedals, right? Because you see a red light. That means now at that moment, your car no longer has apply force because you have your foot, you have your foot lift off from the gas pedal and it's only on the brake pedal. So your car only has friction, which points backward. But which way is your car moving before it comes to a complete stop? Forward or backward? Forward, right? You're still driving forward, you're just slowing down. See? So that's why, like, this is a weird one. So yes, your car is still moving forward, but the only force that's free is actually pointing backward because you're slowing down. Okay? So now that's all the free body diagram. You actually have a worksheet or two to do. I'll put the description on the notes. I know today the lesson is shorter for this part, but I think there are a lot of things that you have to do on the worksheet. Okay, I think there are a lot of things on the worksheet. So I might or might not do Newton's third law. I haven't decided yet, so you will see it. If you see the other video, that means I did Newton's third law too, right? Okay, goodbye.